The number one reason why unwinding the stack matters is actually because of things that aren't on the stack. Things like memory allocated on the free store. When we talked about manual memory management, we talked about the idiom, resource acquisition is initialization. This refers to the idea that when you acquire a resource, like getting some memory off the free store or opening a file or getting a database connection, what you really should be doing is initializing an object. And then the destructor of that object can release the memory, close the file, release the lock, whatever it is that you need to do. We'll use memory as our example, but this logic applies to any resource whatsoever. Take a look at the two pieces of code I'm about to show you. Here, inside a try block, we're allocating something on the free store with new. And I'm using the C++11 feature auto because I don't really care what this is. It's an X pointer, right, with a star, because that's what new X will return. Then some bad things happen, and then at the end of the block, I'm going to delete the pointer. So it's manual memory management. In this circumstance, if there's an exception thrown by the code in risky stuff, the flow of control will go to the catch block, and we will not execute the line that deletes X. This would be a memory leak. You could put delete X in the catch. Two problems with that. One, it's repetitive. Two, if my try block was a little more complicated than what you're seeing here, maybe I don't need to delete X. Maybe we deleted X and then we did some different risky stuff, and it's the deleting of some Y that's getting skipped. You need to have all kinds of if in your, if this is null, and it's nasty. Really is. Some languages cope with this a different way, but in C++, the way to cope with this is not to do manual memory management or anything else manually, but to use resource acquisition as initialization, to create an object on the stack whose destructor will do the cleanup for you. So whether we leave the try block in the normal way, by just reaching the brace bracket and carrying on with our lives, or whether it's because exceptions are thrown, either way there's going to be a destructor going off, and the destructor is going to tidy up. So take a look at this piece of code. Now we're using shared pointers. Make shared, I hope you remember, returns a shared pointer to, in this case, X. And I'm using auto because I don't feel like typing out shared pointer to X. I don't need to hand delete X at the end of my try block because the X now is not a pointer that can have delete called on it. It's a local object allocated, we like to say, on the stack, whose destructor will deal with the free store memory as appropriate. If risky stuff made copies of X, passed it around to other functions that held on to it, and so on, you might not even want to delete X when you get out of here because someone else may still be using it. That's the joy of a smart pointer, a shared pointer. But if you are done with it, it will clean itself up. Now the great stuff is if risky stuff throws an exception, we go out of scope. We unwind the stack. And as part of unwinding the stack, the destructor for X will go off, and that will clean up the memory. So there's no chance of a memory leak. When I covered shared pointers, I said this is super even more useful when exceptions are in play. And now I think you can see why, because otherwise that line to do your manual cleanup would get skipped. You might have to repeat it. Generally, blah. Now, I know that in some other languages, there's a keyword like finally to handle this repeated cleanup. There is no finally in C++. And as you can see, there isn't a need for a finally in C++. If you use this idiom correctly, allocating local stack objects whose destructors will do your cleanup, you don't need a finally. The destructors will do all that work for you. Less code to write and test, and it's also more elegant, which counts for me. It's good performance benefits as well.